Okay, so let me share my screen. Okay, you should see a whiteboard in front of you. You guys can see that?
Yes.
Okay, great. So I have a couple examples here. If you guys, first thing, we're still working on chapter 2, right?
Yeah.
Yes, chapter 2. And last time on Thursday, we solved a couple examples from chapter 2, and they dealt with the hydrostatic force and how you calculate that, and the buoyant force. Right? Are you guys familiar with these two concepts from chapter 2? No questions?
Well, I wasn't here Thursday. I had to go to another thing for a few hours.
Okay, but did you do the homework? And maybe you have a question about buoyant force.
I started on the homework. I didn't do like a lot. I did like more work problems, like energy and work problems. Yeah.
Okay. Okay. So what I have right here, if you guys want, right? So the two important things in chapter 2, or the three most important things in chapter 2, is how you calculate hydrostatic pressure, right? Which is just gamma H if you're calculating gauge pressure. And the next thing is the hydrostatic force. And for this one, you can calculate for a flat surface or a curved surface. And the third thing is buoyant force. That's the third thing in chapter 2. So let's do one example. You guys want to see hydrostatic force on a curved surface? Or are you guys good with that concept?
Yeah, I like to see.
Okay. So I think it stopped sharing. Let me go back really quick. Okay, hopefully it is working now. I have problem 2.86. Hopefully I have it in my images. Yes, I do. So problem 2-86 or 2.86 is asking us to calculate the horizontal force P required to hold the gate stationary, right? Because the water is trying to push on the gate, the hydrostatic force, and we're applying a force P to hold this gate stationary. Okay? You guys good with that problem?
What book are you using?
This problem looks pretty easy. That's good.
Or no, I was asking, what book are you using?
Oh, what book I'm using? I'm using the fluid mechanics book for this class, the one I used when I took this class. That's the one, let me double check. It's just called Fluid Mechanics edition 8, I think. Yeah.
Oh, I thought this was thermal. My bad.
Oh, this is not thermal. Yeah, this is fluid mechanics.
Okay. All right. Cool. I was getting confused. Okay. Well, this is more for next semester for me. So yeah.
Oh,
Anyways,
okay.
well,
All right.
sorry about that.
No problem. Okay, so what about the other people that are joining us? I see 3 people today. I hoped I would see more people because it's Sunday. Hopefully everybody is enjoying or is enjoying their break or their weekend. But yeah, so let's go back to this problem. I think it stopped sharing one more time. Okay. So how would you guys approach this kind of problem? When you have a curved surface, we know how to approach a flat surface. We have 3 equations to find the hydrostatic pressure. We find the magnitude and the location of the hydrostatic pressure. For what about curved surfaces? You guys know how we approach this type of problem?
No. Could you teach us?
Okay, for this one, for curved surfaces, 2 things to like pay attention to is, you see this one right here. This is a horizontal surface, right?
Yes.
So you can calculate, if you have a flat surface like this one, you can calculate the hydrostatic pressure easily because it's just a flat. Disregard this portion for now. What you're seeing here, the dotted or the dashed line, is just a flat surface. So you can easily calculate the hydrostatic pressure. You know the length or the height of the thing is 2 meter. And I think in this problem, they don't give you the width. The width, I think they forgot. The width is 3 meter into the paper or into the board. So width is equal to 3 meters. Well, hopefully this should be simple, right? You have a flat surface. It's a rectangle. And you have the height is 2 meter and the width is 3 meters. Now you can find the hydrostatic force on this flat surface. That's the first thing you do when you're dealing with curved surfaces.
Okay, so find S.
So yeah, let's call it find AH, the horizontal component or the hydrostatic force on this flat surface.
Okay.
And we have a formula for that one, right?
Yes.
Yes, we do. From flat surfaces,
It's gonna be gamma of water times the height times area, correct?
so it'd be, if we're calculating based on gauge pressure, remember, we like to deal with gauge pressures, not absolute pressures. So for FH will be just gamma of water, just call it gamma W, and H times area.
Yeah.
Right, and what is this H right here in the equation?
That's the 2 meters, right?
Is this the entire height of the thing? The 2 meters?
Must be like the center, right?
Oh, the center of
It's
gravity.
HCG. Remember, this is not the entire height of the thing. This is just HCG. I'm not sure if you can see that, but yeah, it is HCG. So, and what's where's the centroid? If you have a, just if you're standing right here in the water and looking directly into this, you're gonna see a huge rectangle, 2 meter by 3 meters. And where's the centroid of this thing?
Halfway point.
Yes, it's in the middle.
But 1 meter.
It would be 1 meter, exactly, yes. So how would you calculate this? How would you find the horizontal hydrostatic force?
For
We know
water,
gamma,
yeah, it's 9790, right?
9790, yes. That's how I like to remember it. 9790 Newton per meter cubed times hcg is 1. And what's the area of this
2 by
rectangle?
3.
2 by 3. And that ends up to be, do you have a calculator?
Yeah.
Times 6. It's 58,740 newtons. So that's your horizontal component. And where does it act, right? Remember, when we're dealing with hydrostatic forces, you need the magnitude, which is what we found right now, and you need the location on which it acts. It's a major thing. If you want to take moment, you need to know where this force acts. So how would you calculate that?
We use the formulas to find the moment first, right?
Yeah, well, first, you need to know the location. We have a formula, or we have an equation to find the location. Remember YCP and XCP? Remember these two formulas?
Yeah.
Oh yeah.
So
Yeah. So let me ask this first. Is this force acting on the centroid of the thing, of this rectangle, 2 by 3 rectangle?
No.
It is not. It is acting where exactly? It's not center of gravity. It's acting on what?
the pressure.
Center of pressure. Exactly.
Pressure,
There's a new concept now. It's center of pressure. Because how like, do you guys know how the pressure distribution looks like on this rectangle? Remember from solid mechanics, if you guys took solid mechanics before and we were dealing with beams, remember? Like a cantilever beam, and then you have like a distributed force like this, and maybe you have a triangular distributed force like this. You guys remember that one?
Yeah.
Yeah, so it's basically the same thing here. We have a huge triangle like this, because remember the pressure is maximum at the bottom. So you have a huge triangle like this. The pressure starts at 0 at the top and ends at the maximum value at the bottom. And how do you, where is the centroid of that triangle?
2/3.
It's not exactly in the center.
2/3 from the.
Yeah, it'll be, I think, one third, right? Or 2/3. Yes, it is.
From the, yeah.
So, well, it depends. Like it's 2/3 from all the way from the top, and it's 1/3 from the bottom.
Right.
Right. So you can use the formulas YCP and XCP. That's totally fine. But how I look at this problem is just basically a triangle. And where is the centroid of this triangle? It would be 1/3 from the bottom or 2/3 from the top. And that's the centroid of this triangle, which is the center of pressure of the flat surface. So let's go from the top, 2/3 from the top. Two-thirds H. Good?
Yep.
Oh, so you can use like the YCP, the XCP, but you can also use this, right?
Yeah, well, sometimes it's simple like this. Because you know the pressure distribution, the pressure is 0 at the top, and it varies linearly, right? Until it reaches the maximum value at the bottom. right? So the centroid of this triangle will be the center of pressure on the flat surface. Or if you don't want to like visualize all this, you can use YCP and XCP. That's totally fine. You'll end up with the same value. But remember, YCP, when you get a value for YCP, I think I got kind of confused last meeting on Thursday. When you get YCP, let's assume it's 0.5 meters. What does that mean? 0.5 meters. Where should I begin? Should I begin from the bottom and move 0.5 meters to the top, or begin from the top and move 0.5 meters to the bottom?
You start from the HCG.
Yes, it will. You should move 0.5 meters downwards, because remember there is a negative sign
Right.
in YCP. There is a negative sign. So if you got negative 0.5, you would move 0.5 meters downward from CG, from the centroid. Yeah.
Okay, yeah. I figured that out after.
Yes, yeah. Yeah, I got kind of confused last meeting. I apologize. But yeah, you move 0.5 meters from the centroid. But for this one, it's 2/3 times 2, which is, I think, 1.3, 1.33. Okay, so that way we know the location of center of pressure, and we know the magnitude. Now we're basically done with the horizontal component. We should move to the vertical component right now, which is caused by what? What's causing this vertical component we're going to calculate? So we have this vertical component right here. What's causing this vertical component? Guys, you know, you can guess. You can guess. You can.
It's just
Gravity?
the weight of the water.
Yeah, it's just the weight of the water on the gate, right? This curved surface has water filled in its cavity, so this weight of the water is pushing downward on the gate. That's why this vertical component is there. Okay, so let's call this one FV. And it's basically, this is just the weight of the water, of this right here. So let me try to make it look better. Use a different color right here.
So does the word gate, does that just mean like, is that like a specific like term for fluid mechanics, or?
No, it's literally just a gate.
So
Like
just
a gate.
just contains it, right? Or
Yeah.
yeah, okay.
Yeah, it is it's like a dam, right? You can consider this like a dam.
Yeah, okay.
It still works. Mostly civil engineers are mostly concerned with these type of problems, but still, because you remember, civil engineers still take fluid mechanics. Okay, so this section is filled with water here, and the weight of the water in this section only is pushing downward on the gate. So how would you calculate the weight of the water? First thing, it's
water.
yes, it's a force. So we should end up with what unit if we're calculating a force?
Newtons.
Newtons. Okay. And how do you, by looking at this problem, you have you're given basically h, right? You're given h. So what is that? It's basically the radius, right? For this quarter circle.
Yep.
It's basically the radius. Okay. Well, that's good. We have gamma, right? Gamma is really important because it's called specific weight. So maybe we should include gamma in our formula. And what's the units for gamma?
Newtons per square cube. Right?
So it is Newton per meter cubed.
Meter cube.
Okay, well, that's great. We need this Newton right here. We need to get rid of this meter cubed. How do we do that?
Volume?
Yes, multiply gamma times volume, you'll end up with Newton, and that way you calculate the force.
Yep.
That's great. That's one of the first thing to remember in fluid mechanics. It's all units, right? I have gamma. I need this Newton from gamma. I just only thing I need to get rid of this meter cubed. Okay, so just multiply times volume, you'll end up with Newton. So it is gamma of water times the volume of this quarter circle. So let's go with volume of water, W. And we shouldn't end up with Newton because it's a force.
Mm.
So let's plug in numbers for this one. We know gamma of water is 9790. And then this is Newton per meter cubed. And then you multiply this one times the volume. How would you calculate the volume of water in this case? You guys know?
It'd be pi times 2 squared over 4 times 3, because
Yes,
the volume of the little quarter circle.
exactly. So pi, I want to use diameter, so pi over 4 times 2 squared. Remember, and it's three-dimensional, so times 3 by the times the width. And now you end up with the volume. And this should be in meter cubed. So meter cubed will be canceled and you'll end up with Newton, and that's the weight of the water. Any questions, guys? So far, so good? So if you do the calculation, you can punch in the numbers in your calculator. I got 92,270 newtons. Good.
Yep.
And we need the location of this force. We found the magnitude, remember, right? For the horizontal one, we did find the center of pressure. For this one, we need to find also the location of this force. And where does weight act?
Centroid?
The centroid, and the centroid of what? The centroid of our,
Quarter circle?
yes, exactly. So it would be somewhere right here. Let me use a different, I'll use a green. So the centroid of the thing, of the quarter circle, will be here.
Mm-hmm.
And here's your FV.
Mm-hmm.
And how do you find this location? How do you find the centroid of a quarter circle? Do we have to start deriving equations? Not really, right? Remember in chapter 2, I can share my screen and show you guys. In chapter 2, if we go to my screen right here, you can see the book now, right?
Yep.
Okay, so if you go to chapter 2 and you go to hydrostatic forces, that is section 2.5, and there you go. You have a semicircle. We don't have a quarter circle, but it's basically the same thing, right? It will still be 4r over 3 pi. And it's somewhere here. So if you consider this quarter circle, the centroid will be here, and the height will be 4r over 3 pi.
Mm-hmm.
Okay, or you can use your solid mechanics textbook and find the, I'm pretty sure it's listed in there for a quarter circle, so you don't have to start deriving stuff. Everything has been derived before. Okay, so let's go back to the whiteboard. Okay, so if you do the calculation 4r over 3 pi to find the location of the centroid of this quarter circle, you'll end up with a value 0.4849 meter. Right, and this is starting from C. So you need to go, let's draw an arrow here. So you go from C to the centroid by 0.849 meter. And now it's easy. Now we know all the locations, we know all the magnitudes. We can write the moment equation at point C. And it should equal to 0, right, to hold. So it's a static problem. And can someone tell me the equation? Or this one? How would you find, first thing, how many forces are we dealing with in this problem?
2. Oh, wait. 3.
Yes, yes, including P.
Yeah.
Right, that's good. Okay, well, we know we have 3 forces, so we're probably gonna have 3 terms in the moment equation. And all we have to do is multiply each force with what?
The distance.
Distance, exactly. So let's do P first, because it's simple. And let's assume clockwise is negative. So counterclockwise is positive, and clockwise is negative. So from point C to P, what's the distance?
2.
2.
2 meters.
And it should be negative.
Yeah.
Right? It should be negative 2P. And then for FH,
Well, we have the distance at 2/3 from the bottom, right? 1/3 from the bottom. I mean.
yeah, it is 2/3 from the top and
Top,
1/3
yeah.
from the bottom. So do we add or subtract? though?
We add.
You add,
Add.
exactly, yes. You add FH, which is, I'm not going to write the magnitude, so I'm just going to write it FH times 1/3, which is,
1/3 of 2.
no, it's
1/3.
It's like 1.667. Oh, wait.
Just be 0.667.
yeah, 1/3 times, I'm trying to do it like 1/3 times 2, which is 0.667. Because remember, it's 2/3 H and from the top and 1/3 H from the bottom, and H is 2. Okay, and then this is positive. What about FV? Should we add or subtract for that one?
Add.
Add, so FV times, I think we calculated the value. Yeah, 0.849. 849. And you equate this to 0, and we basically know this one, and we know that one. You basically solve for P, this one. And you should end up with a value, if you do the calculation, 58.7 kilonewtons.
Mm.
That's the final value for P. And that's how you approach problem with a curved surface. You have to split it. Otherwise, it's going to be tough to do it. And sometimes you need a computer program to do it. But this, if you have a curved surface, split the force. You have a vertical force coming from the weight, and you have a horizontal force coming from hydrostatic pressure.
Oh,
Yeah, and I think literally you can do 90% of the problems if you have a curved surface using this approach, really.
look for the the horizontal force first, and then move to the curve part, right?
Yeah, first thing, find it as if it's a flat surface, then move to the curved part and find the weight of the water in that curved part. Because it's pushing on the gate, the weight of the water.
Okay.
Okay.
So, so for the horizontal part, you can find the YCP by just using the pressure distribution and finding the center out of the shape of that.
Yes.
Yeah.
You can.
Okay.
Yes. You can, because on a flat surface, that's how the pressure distribution is. It's a triangle, right?
Cool.
Yeah, because it starts at 0 and it's maximum at the bottom, so we know it's a triangle. It's not going to be a rectangle because the pressure is not constant. It varies linearly as you go deeper.
Yeah, that's a lot nicer than using the formula. It's
Yes.
really quick.
Yeah, this one is easy. I think it stopped sharing, but this one is easy because it's just a flat surface, right? And I know the pressure distribution is going to be a triangle. Okay, and where is the centroid of a triangle? Back from statics. I remember it's 1/3 from the bottom or 2/3 from the top. So I can go with that. Or if I don't want to, I have a complex geometry, I can use YCP and XCP and be done with the problem. I don't have to think about it.
Okay. Thanks.
Okay, good. Sometimes it's good to use like a what do you call it? Like an easy way to solve the problem. And if it's too confusing, use equations. Always use equations. You don't have to think about this.
So if they ask for, like, for example, what is the pressure on the bottom of this system?
The pressure on the bottom, we mean right here?
Yeah.
How do you calculate the pressure here?
Do you just do like a regular um, like the pressure, high pressure equation?
Yeah, it's you want to calculate the pressure at that point specifically.
Right.
Okay, it's basically gamma h,
Just gamma h.
just gamma h, which is h will be 2 in this case here because you're calculating the pressure right at the bottom, 2 meters.
Oh, okay. So it just depends on the. It's just
Yeah.
different because this is the curve. Okay.
Yes.
Oh,
So if you look at this one, right, and what's the pressure at this point, right at the top?
that's what we found, right?
The gauge pressure
Oh,
at the top. It would be what?
like
Remember?
the P that we found?
No. What's the? I'm just asking. What's the pressure at the? Not P. P is a force, but I'm asking what's the pressure at this point, right at the top, ambient conditions.
Oh, that's ATM.
Yeah.
Like
So it's
pressure
basically if you're measuring gauge pressure, because that's
Right.
what we like to deal with. It's basically
Mhm.
0.
Mhm.
And what's the pressure right at the bottom? At the 2 meter at point C, what's the pressure at this location?
And there'll be
It will be
rho P.
gamma H, or
Yeah.
gamma times 2. Okay, what about what's the pressure at this specific point right here? And let's assume it's 1.33 meters.
Wait, where? I don't see.
Right here.
Oh, okay.
At this point, and I tell you the height, it's 1.33 meters, so you multiply gamma times 1.33, you end up with the pressure value. And you kind of see if you want to do it for all points, you'll basically end up with the triangle with the maximum pressure at the bottom. Good?
Gotcha. Yeah, I get it now.
Okay.
Cool. Thank you.
And I have, so I think, any questions about curved surfaces, guys? Any problem you saw from the homework or anything? Because yeah, you can always ask me. I'm not a professor. I don't report any student to the professor. I'm just talk, just ask, guess. You can do whatever you want really, as long as you're hopefully you're finding these sessions to be helpful.
We do a buoyancy problem. You said three things to learn in this chapter are the buoyancy problems, like hydrostatic forces, like for curved and non-curved, and then you said hydrostatic pressure, right?
Exactly. Yes.
Okay.
That's basically this whole chapter. There's 3 main concepts.
Okay. Yeah. Yeah. So could we do a buoyancy problem?
Yeah, sure. Let's do the final thing. Or I remember for this chapter too, don't forget manometers. You guys remember that one with all the tubes and
Mm-hmm.
you guys
Oh,
remember? Yeah. And how you move from one point to another point. Yeah, so remember, it's basically hydrostatic pressure, right? Because you're just multiplying gamma times h.
Mhm.
But yeah, make sure you know that concept. I'm pretty sure professors like to ask these questions. Okay, so I'm trying to, let me add a new page. And I think, trying to click on it. Okay, I don't think I have a picture, but I know the problem because I worked on it yesterday. It's problem 2.117. So problem 2.117. Is this problem from your homework? You guys remember? 2.117. I'm not sure.
My class has the connect thing.
Yeah, it's in my homework. It's like an iron ball.
Yes, it is an iron ball. And you're from Professor Armand's class, right?
Yeah.
Cool. And we have, do we have any student from different professor?
Yeah. I think I have. Wait 1 sec.
I think Dr. Henry is teaching a class definitely this semester. And I'm not sure who the third professor is. Okay, but yeah, I don't have a picture for this problem, but I can draw it because it's simple. You just have a
Oh, I have
cable.
Wardak. Sorry,
Oh,
I have
you have Professor Wardak. Okay. Okay, cool. And you're still working on chapter 2, right? Or did
No.
you move to chapter 3?
Yeah, I think we're on chapter 3 now.
Chapter 3. Okay, hopefully on Tuesday, I can have more examples and notes from chapter 3.
Yeah.
Okay, but let's go with this one. You basically have what, a tension cable holding an iron ball in water, and this ball is submerged in water. Let's see, water, and this one is iron. And basically you have a tension cable just holding this iron ball in water. Okay, and what's the problem asking? We need to find the diameter in this iron ball. So find the D, find the diameter, given that the tension in the cable, this cable, is equal to 600 pound force. Okay, it is a 600 pound force. What else is given? We need something, I remember. We need specific gravity of this iron ball. Specific gravity is 7.9. Okay. So do we have all the givens? We have tension, and we have specific gravity, and we're looking for diameter. Yes, so that's the problem.
Yep.
Okay. How would you approach this problem? Well, I'm gonna tell you from now. We're dealing with a buoyancy here. We're dealing with a buoyant force, right? Because it's completely submerged in water, and of course the water is trying to push up or has a buoyant force on the iron, pushing it up. And how would you approach this problem then?
By
I think
direction.
the formula for buoyancy is buoyancy equals specific weight times volume, right? Something like that.
Yes, it's specific weight of the fluid times the volume of the submerged object.
Yeah.
Right? Yeah, that's the definition of the buoyant force. And make sure you label all these things, right? Don't just write specific weight times volume. You'll be so confused. I remember when I took this class, like, okay, remember for hydrostatic and forces on a curved surface, right? I had to write HCG. Otherwise, for H, I would use 2. Remember from our last problem? If you write H, so let me go back to it really quick. if you, it's down here. If you write H for this one, just H, you'll use 2 instead of 1. So that's why we write HCG. That way we know, okay, it's the centroid, so we have to use 1 meter. Otherwise, if you use 2, your entire calculation will be wrong. That's how I like to label stuff. And what is area? Right, I think for area we have to label it too. This is the area of the flat surface. So make sure you label all these kind of you'll notice, like, once we jump into chapter 5 and 6, or chapter 5, I remember, you'll have so many different variables. It's crazy. So you're gonna have to label them. Okay, so that's just a side note. We can go back to the problem and see. Let me write down. So the buoyant force is gonna be equal to the specific weight of the fluid times what, the volume
Of the object.
of the object. Yes. And remember, the volume of the object submerged in the water. If we have, I think the book mentioned this. I was reading the chapter 2 yesterday, and what if you have like a ball like this? Half of it is under the water, is submerged in water, and half of it is sticking out in the air. How would you calculate the buoyant force on this thing? Well, you would use specific weight for the fluid. Specific weight will not change, but the volume of the object, should we use
Half of it, right?
half of it? Only the volume submerged in the water. In our example, or in our problem, it's simple because the entire object is in the water. But what if we have something like this? Half of it is sticking out and half of it is submerged in water. Then you have to only count for the half submerged in the water. That's your volume. Okay. And this was also a side note, because I was reading the chapter yesterday, and some problems deal with this type of thing. So I'm just grabbing your attention to this. Okay. Well, let's do this problem then. And I know it's 2:50 right now, or 2:48, but are you guys okay if we went overtime, like 15 minutes, just to solve this problem?
Yeah, I'm good.
Okay,
Yeah.
great. Yeah, I will try to.
Yeah.
Because I talk a lot and waste a lot of time. So hopefully on Tuesday I will not do that. But yeah, let's go over this problem. So how would you approach this problem? First thing, we have to draw a free body diagram, right? So imagine this is your iron ball, and what are the forces acting on it?
Weight.
You have weight, right, at the centroid. There is weight. And what else?
Buoyancy pushing up.
You have buoyancy pushing up. FB. And what else you have?
Is that a cable? Then tension, right?
Yes, you have tension in the cable, which is 600. 600-pound force, tension in the cable. Great.
Yep.
Yeah.
So how would you write the summation of forces in the y direction?
Mhm.
It should equal to 0, right? Nothing is moving in this problem. So it should be tension is equal to buoyant force plus weight.
Yep.
Okay, great. So let's move to just plugging in values. 600
Wait,
Wait,
wouldn't it be? Yeah, I think it'd be minus.
yeah.
It would
You
be
got, yeah, minus.
minus, yes, should be T plus FB is equal to weight,
Yes.
right? Yeah, I think yes, it is, because they're both acting, yes. Should be like this. Yeah. Yeah, good catch. Yeah, I think it's 600. Yes, it is. T plus FB is equal to weight. Okay, and if you plug in 600, and I think let's deal with SI units. That's how I solve the problem. Let's work with SI units. So how do you convert pound force to newtons? Pound force. I know 1 pound force is equal to 4.45 Newton.
Hmm.
That's the conversion value. You multiply 600 times 4.45, you end up with 2,670 newtons.
Mm.
It's just a conversion value, yeah. Okay. So let's see, 2,670 plus, what's FB in this case?
Gamma of the fluid.
This equation, right?
Yeah.
So it's gamma fluid times the volume of the object. What's the volume of our object? It's completely submerged in water.
Sphere.
It's a sphere, yes, the volume of sphere, I think it's 4 pi over 3 times r cubed. This is right, 4r cubed. Yeah, yeah, it is r cubed. That's the volume of the sphere. And what about weight? With the weight of this iron sphere? How would you find that? Well, first thing, what's the unit for weight? That's how I solve these kind of problems. What's the unit for weight?
Newton.
Newton, exactly, because it's just weight is just a force. So we need to end up with a with Newton because it's a force. And what is weight? If you remember from maybe dynamics, or how would you find weight or statics? It's basically just mass times gravity, right? That's how you end up with weight. Okay, great. So we need this. We know gravity is a constant value. It's just 9.81. We need to find mass. If we find mass, we find the weight. How would you find mass in this problem, given these values like tension and specific gravity?
Tension. No, wait. Mg wouldn't be. No, I'm not sure.
I haven't played in a while.
Okay, so if you look at a specific gravity, oh, we hear gravity. So maybe it can help us. What is SG? What's the formula for SG? Specific gravity.
Density of fluid
Exactly. Density of the fluid
over water. Density of
over
water.
density of the water. Or in this case, our fluid is the iron ball itself.
Yeah.
Right? So, and this one is 7.9. right?
Oh, you should multiply by G.
So maybe if we take out this one, and this is the density of the iron ball. So if it's how would you find density of the iron ball? You just multiply 7.9 times density of the water. And what's the density of the water?
1,000?
Yeah, 1,000 is good. I think I used 980 and 998, not 980, 998, or 1,000. It works. So you
So
end up with,
specific gravity is always like it's a ratio always for with water, the specific gravity of water.
yes, if you have a fluid, if you have gas, it's gonna be the density of air, right? But in this case, we have water, right? So it's a fluid, so it is over density of water. It's just comparing the two ratios. And we got 7.9, which is much larger than 1. That means the iron ball will actually start sinking, right? It's much more dense than water. That's why we have tension in the cable. Okay?
Oh, okay. And then we can solve for
Yes,
mass.
so this one is 7,000 something, 7,900? Is this good? Yeah, 7,900. And that's, what's the units? I like to carry units because the way I solve this problem is just by looking at units. Remember, we need something with Newton. So this one is 7,900. Should be what?
Newton meter squared.
Mass over volume for density. Kilogram per meter cubed. That's a unit for density. Okay.
But kilograms per meter squared is in Newton, right? Or
no, well, we have gravity is right here, so all we have to do is solve for mass. And what's the unit for mass in SI system?
Kilograms?
It's just kilogram.
Yep.
Right? What's the mass is basically in kilogram. You multiply kilogram times gravity, which is meter per second squared, you end up with Newton. That's the definition of Newton.
Yeah.
Okay, so how do we get from this one to this one to only kilogram?
You multiply by volume.
Exactly. Perfect. Yes, you need to get rid of this meter cubed. So you multiply this one times the volume of what?
The iron ball.
Of the iron ball, which is going back to the previous one, it's 4/3 pi r cubed. And this is going to be meter cubed because it's a volume. And these two units cancel. Now you have kilogram.
that's pretty cool that you just solved it from like the units.
Yes, there's a whole chapter in fluid mechanics called I think dimensionless analysis or something. I forgot. It is in there. I don't know which chapter it is. Dimensional analysis, right here, chapter 5. Dimensional analysis, basically you solve the entire problem using just dimensions. And we'll get there eventually, but I mean very powerful. I use this for even heat transfer. It's a very powerful tool. Okay, great. So you just plug in values now. So if we go back, it's 2,670 plus, I'm just rewriting this equation. The gamma of water, we said it's I think we calculated it somewhere. Yes, it's 7,900 times 4 over 3 pi r cubed is equal to what? The density of iron?
Hmm.
No, this is wrong right here, right? Specific weight of the fluid, not the density of water, or not the density of iron. So what's the specific weight of water? It's basically 9,790, right? That specific weight times volume is equal to mass times gravity. And that's how we found mass. It's basically density, 7,900 times 4 over 3 pi cubed r cubed times gravity, 9.81. Am I missing something?
I think like what are you looking for in this one? B, right?
We
But
need diameter.
you need the SG for water because you're looking for gamma of the fluid, right?
Well, gamma of the fluid is water.
All of the fluid will be water, right? Oh, okay.
Yeah, so this gamma fluid, remember this iron ball is submerged in water. So this
Right.
fluid should read water. It's not fluid, it should read water.
Because
Any,
right
yeah.
here, the row of iron, when you found SG, right? Aren't you finding
SG is given in the problem, 7.9.
that you have that using the density of iron, right, over water to find the density of iron? Would
Yes,
iron, you wouldn't be like the gamma for the iron then?
it would be the gamma of the iron.
Yeah, would it be the gamma of iron? Or no?
If you do what? Because remember, specific gravity, you can use gammas or you can use densities.
Mm-hmm.
Right? You can say SG is equal to gamma iron over gamma water, or you can use density of iron over density of water.
Right.
You will end up with the same result, but it's just you calculate two different things. That's it.
Okay.
Okay, and for this one, I found the density of iron. Why? Because I know density is mass over volume. I need this mass. That's why I found density.
Mm-hmm. I was talking for the left side, right? For the FB part, not the weight part.
This
That's
one?
the FB. Yeah, like where you have the 9790.
Oh, oh, this one you mean?
Yeah, I'm talking about that part, not the right
Okay,
part.
I'm rewriting. So let me.
So that's for water, right?
Yes, I'm rewriting this equation. So the specific, remember the buoyant force, that's the definition of the buoyant force.
Oh, that
right
would be
here.
from the fluid that is submerged. The iron is
Yes.
submerged on, not the. Oh, okay, gotcha.
Yes, it's the gamma of the fluid. Remember, you have water, and the volume of the object in this fluid.
Okay.
That's why I used gamma of water, because our fluid is water.
Gotcha. Oh, okay. So you just found the SG equation just to find the density.
I just used SG to find density of iron because I need the mass.
Gotcha. Now I get it. Okay.
Yeah, nothing else. You can approach this problem in so many different ways, but that's how I like to approach it. What is weight? Weight is basically mass times gravity. Okay, gravity is constant. We can assume it's constant, 9.81. And mass, you can find it from density, because I know the definition of density is just mass over volume.
Okay.
Yeah. Okay, and you have now this equation. I think that's. I think we should be done, right? Because we only have one variable, which is the radius of the iron ball.
Mhm.
So these right here and right there. If you do the calculation, right, you do all the calculation. Maybe you want to plug it into your graphing calculator, or you can solve it by hand. Very easy. You'll end up with a value that is equal. Let me move this just a bit. So R is going to be equal to that's the radius of the iron ball, 0.2113. And what's the unit for this one?
Meters.
It is going to be meters, exactly. Why do you know it's going to be meters, though? How did you know?
Because all your units are in meters.
Exactly. I converted the entire problem from pound force. I used kilogram for mass. I used meter cubed for volume. So my value should end up in meter. That's how you double check your solution. I can't write meters now. Okay, and that's radius. Remember, the problem is asking for diameter. So you basically multiply this times 2, you end up with 0.4226 meters. And if you want to convert, I don't know, I guess they went to centimeters too. So you can, how do you convert from meter to centimeter?
Divided by 100.
You multiply by 100.
Oh, multiply, sorry.
Right? You multiply because meter is larger than centimeters.
Yeah.
So 42.26 centimeters. And that's your final answer. And that's a pretty good problem, actually, to deal with the buoyant force.
Okay.
Yeah, I went 20 minutes overtime. But was it helpful, at least, guys?
Yeah, it was helpful.
Any questions?
So
very
for the last two lectures, are they posted somewhere? Because I wasn't able to make those.
I
see that you're like recording these.
I have them on my computer. I record them for myself, or sometimes they require me to record them. But I can post them if you can give me your email, or I was hoping to set up a Discord server if you guys are interested.
Yeah, okay.
Yep.
That's fine. That'd be great.
Okay. You guys wanna give me your tag on Discord or your username so I can add you and hopefully set up a server?
Sure.
Okay, you can post it in chat and hopefully I can add you, right? I do hope to see more people on Tuesday too. So we can set up a Discord, and maybe if you're doing a homework problem and you need help or something, yeah, we can help each other. That's totally fine. Okay, so that's my tag on Discord. Let me try. How about you guys add me? Because till this day, I don't know how to add people on Discord. Okay, so I see. Okay, let me open the chat one more time.
I already added you as a friend, so you can just add.
I did add you, Carlos, right? From the
Yeah.
previous meeting? Yes. Okay, I sent one right now to, how do you pronounce your name? Tenzin or Tenzin?
Yeah, Tenzin.
Tenzin, okay. And let me add Nick too. For some reason, I can't add you, Nick. I don't know. I always have problems adding people in Discord. But you can add me, and
Yeah.
I'll set up a server and call it ME3111. And if you're working on homework problems, you need some help, something, yeah, you can text, and hopefully I can help you same day. Okay.
Thank you.
Okay, so I have all. Okay, great. So I'll see you guys on Tuesday, hopefully.
Okay.
Right, take
Thanks.
care. Bye.
See you.